Hi, welcome back. And we were talking about population growth, and particularly human population growth. And we're worried about trying to predict how the human population is going to change and when it's going to stop growing and what's going to happen. And we talked about using an equation to do this. In fact, your textbook gives you several population growth models. There's the exponential population growth model. There's the logistic population growth model. And typically what textbooks do is they just throw a mathematical formula at you and expect you to understand it. But the best way to understand any mathematical model is to actually see where it comes from. So that's what we're going to do today. We're going to figure out where this logistic population growth model comes from that your textbook has. And remember, we got to start out with the idea that populations don't grow exponentially. But for a quick review, the exponential growth model has important parts of it that we need to understand. First, there's the idea that we're trying to model the change in population size. And your textbook says dn over dt, which is the change in the number of individuals over the change in time. And we can think of this as, the number of females in the population, n, and this is the number of years, say, the change in years. Your textbook also uses this term per capita growth rate. Now, what the heck does that mean? That's fancy. Well, per capita comes from Latin. Basically, it means per head. And if you think about it, each person has one head, so what it means is per person. So this is the rate of growth per person, but really it's a function of two things, the birth rate and the death rate. And we typically think about the births that females give, because females are the only ones that give birth, and the death rate of females. And if you want to know the whole population size, you can multiply it by 2, assuming that there are as many males as females. So these values are going to be quite small, typically less than 1. And that's because, my wife isn't going to have a kid every year, and she's probably not going to die this year. So these chances, these rates, are going to be very small, but it's the difference between them that matters. And of course, as births are greater than deaths, then the population grows. And you multiply that against the current population size. Now, you guys know that what happens in this kind of model, which your textbook simplifies to look like this, is that if R is positive, the population grows exponentially. In other words, over time, if we have time here, and this is the population size, it grows like that. But what really is much more likely is that a population will slow down and start to grow like this. And that's what we want. We want a model that works like that, so we can predict when populations will start to slow down. Now, the reason why the populations grow exponential in the model that we already discussed is that we're assuming that the births and death rates don't change. So this value R, the per capita growth rate, doesn't change as the population grows. There's no density dependence. That is, R doesn't depend on density. But it's much more realistic to assume that there is some density dependence, that as there's more and more people on the planet, it's going to be harder and harder to have babies, and it's going to be more and easier to die. Because there's going to be an accumulation of waste, there's going to be war, there's going to be famine, there's going to be disease, and all these things are bad for reproduction and good for death. So if we think about it, we can build a model, and the simplest model we can build is just where there's a linear decrease in the per capita growth rate as the population increases. And at some point, we hit a population size where that population doesn't grow anymore, and that's because the birth rate equals the death rate. And that's the carrying capacity of the population, or K. Now, your textbook gives you a model of population growth. In fact, it looks something like this. It looks just like this. And you can look at that and go, well, it kind of looks familiar because I see that the change in population size is equal to Rn, but there's all this other junk on the other side. Where the heck does that come from? Well, it basically comes from just making this assumption here, that there's a linear decrease in the per capita rate of growth as the population grows. And I'm going to show you how that happens. Now, let's just make this really simple to look at. This is really what's on that axis. This is the population size, n, and this is the per capita growth rate. It's the growth rate per individual, in this case per female. And we're going to assume that growth rate starts out at R, but as the population grows, it decreases to 0, and it hits 0 when the population size equals K. Now, all you need is 8th or 9th grade algebra skills to actually turn this graph into the mathematical model that's in your textbook. So let's see. I'm going to stick it all the way up in the corner, and it's always going to be here in case you need to refer to it. But what we're going to do is now put this into a mathematical equation. How do we do that? Well, it's simple. All this is a line. So all we need to do is find the equation for a line, and that's y equals mx plus b, where m is the slope and b is the intercept, right? And you guys should be able to think way, way back to your math class as to how do you get the slope and the intercept from a graph. So the intercept's easy. Let's start there. The intercept, or b, is basically the value of y when the value of x is 0. So if x is n, we want to trace all the way back to that point and say, what's the value of y? Well, that's r. And so we've got that part. Now the slope. Well, that's a little harder. In that case, we're going to have to figure out what we used to say in algebra as the rise over the run, or the change in y over the change in x. That will be equal to the slope. And what's y? Y is going to be equal to what's on this axis. 1 over n dn dt, or the growth rate per female. Now all we need to do is actually figure out what that slope is and put it in there, and then we'll see it boils down to the same equation that's in your textbook. So how do we get the rise over the run, or the change in y over change in x? We need 2 points to compare y and x with. So here's a point here, and here's a point there. And you can see that the value of y at this first point is equal to 0. And the value of y at the second point is equal to r. So the rise is 0 minus r. We could also take the x value at this point, which is k, and the x value at this point, which is 0. So the rise over the run, or the change in y over the change in x, is 0 minus r over k minus 0. Now I'm just going to boil that down to minus r over k. And now we're going to plug that into there and see what happens. Okay, let's write this all out plugged in before we move on. Great. This is the model. But that doesn't look anything like what's in your textbook. Well, that's because your textbook simplified it. So let's simplify this equation. I'm just going to rewrite it here. Oops, mistake. Those happen. Okay, now to simplify it, the first thing we might do is basically bring this over to the other side. So we're going to multiply this side by n, or both sides by n. This becomes dn dt equals minus r over k n squared plus rn. So you can see just by multiplying this side by n disappears on the left, and we get n squared, and we have to add rn here. Now, you could see right away we can factor some stuff out, and of course that's what the makers of your textbook did. So they factored out both r and n from this side. And so you end up getting r n, and if you factor that out here, it's minus n over k. And if you factor out rn from the next term, it's just 1. And this is going to look really close to what's in your textbook. And so if I bring it on up to the top and write it out, just rearrange what's in the parenthesis, it's exactly what's in your text. The change in population is equal to r times n times 1 minus n over k. When you hit an n that's equal to the carrying capacity, you see that you get k over k, and it's 1 minus 0. Sorry, 1 minus 1, my mistake, and that's 0, which means the population stopped growing because anything times 0 equals 0, right? So dn dt equals 0. But if you have a very, very small population, say 1, then k is essentially very close to 0, and this value in the parenthesis is 1, and now you get rn. So the model works the way we'd expect. But we also see where the model came from. And that's the beauty of being able to just use a little bit of algebra to figure out where things come from. Now you understand that this model is nothing more than this assumption here turned into a mathematical equation. Okay, we'll talk in breakout and in class about how we can use this model to predict how populations will grow if we have information about the human carrying capacity. See you guys next time.